Okay, so hello again, everyone. Today we will talk about the complex numbers. I will try to keep it short, but there are lots of important features and the definitions that we really need to know in complex numbers so that we are fully prepared. Okay, I'm using notes online. Well, you see on the screen. I will not say the name. So I will use these two chapters here about the complex numbers and the further complex numbers. Each of them has three sections. We will talk about the introduction to complex numbers. What are they? How they work? What are the key notions about them? Then we will talk about the modus argument form. What's that? How we find it? And then introduction to Argand diagrams a little bit. After that, we will talk about the geometry of complex numbers, again, very shortly. And finally, and most importantly, in my opinion, would be the forms of complex numbers. I'm not going to go into the applications of complex numbers, which is basically how to find the sum of sinusoidal functions by using forms of complex numbers. I will not go into that detail because it's a high level in my opinion. I'm not so sure exactly if it's high level in IB, but I think it is. Anyways, I will not go to that yet, but if you would like me to explain it, I will do so in another lecture, maybe in my office hours. Both is okay. So let's start. So introduction to complex numbers. What are they? So first of all, we need to know what's an imaginary number. Oops, that's my phone. That's my mom actually. Uh, what's an imaginary number? The imaginary number is the number that we call, which is under the root, and it's defined to be -1. But actually, imaginary number is any number with negative sign under the root. Okay, but it could also have a real part as well. So a complex number, it could have a real part as well. So you could have, for example, 2 plus root minus I, but this part would be imaginary. Okay. Because why we call it imaginary? Because as you know from the real numbers, until now we were always dealing with the numbers under the root which are bigger than 0, either 0 or something bigger than 0. So 2, 3, 1, 2.1, anything that's positive. We never dealt with the numbers which are negative under the root. And that's how we define an imaginary number. Okay. So imagine number I, we define this as to be I. So let me delete everything. So, and it's defined to be root of -1, which means if you take a square of it, so I square will become -1 because then the square root will go away because you're taking a square of a number. Then you will have a -1. Okay. So what's a complex number? Well, complex number, as we said, is a number with both real part and the imaginary part. For example, you could have 3 plus 2i, right? So this I here is the imaginary number. It could be like, for example, 7 minus 2i. It could be, for example, 4i itself, right? So what's the real part of 4i? It's just 0. Because we don't write it, of course, because there's no need to write 0 plus something because, you know, it doesn't have any role in the addition. But if you really have to be specific, then 0 would be a real part of this complex number. Okay, imaginary part of this complex number would be 4i. Okay, and then we are going to go into more detail. To be more precise, we don't call 4i to be the imaginary part, even though we know that I is the imaginary number. We call only 4 to be the imaginary part of your complex number. So we define it in the following way. We write down real, so let's say that your complex number, which is usually denoted by z, okay? It could be any other number, by the way, but we usually denote it by z. And let's say that it has a form a plus bi. What does this mean? The important part is, of course, I. It's an imaginary number, and a and b is any real number that you want to choose. It could be fractional, it could be with quadratic, like something under the root, of course, positive. It could be anything that you want. It's just a real number. And then if you're looking for the real part, which we denote at R and E of your complex number, then you write that it's A. Because this is the number that doesn't have any I attached to it. If you are looking for imaginary part, you denote it as the I and M of your complex number, then you write it's B. Not BI, okay, it's very important, it's just B, okay. because that's the number that you are multiplying with the imaginary number, right? Okay. What else? So what's the Cartesian form? The form that I have written here is defined to be the Cartesian form. This is the first definition and the first thing that you would probably have to memorize. This is the Cartesian form of a complex number. Okay, z equals to a plus bi is your Cartesian form. Again, a and b are real numbers, and I is an imaginary number, which is defined to be root of -1. Okay. What else we have here? Some examples. Maybe let's have a look. Actually, it's okay. We can have a look at the examples later. So how do we add and subtract or multiply complex numbers? It's quite easy, actually. Let's go through the examples. Okay, let's say that our first complex number is 2 plus 3i, and the second one is, well, it could be anything. Let's say 1 plus 2i. Let's say that we are adding them. When we are adding them, well, of course, since we cannot mix the real part and the imaginary part, right, we have to deal with them separately. So if we are adding them, which means we have to add the real part separately. So 2 plus 1 is 3, and the imaginary parts separately, which will make it 5i. So that will be the addition, how the addition works. If you want to find the subtraction, again, with the same complex number, let's say 2 plus 3i, minus 1 minus 2i. Well, it works the same way as well. You first deal with the real part. So you have 2 and 1, but there's a negative sign in front. So it will become 1. Then you have 3i and minus 2i, but there's another minus here, which will make it plus. So you will have 3i plus 2i, and that will be basically 5i. So this would be your subtraction. By the way, I made a mistake here. This is not 5i because we have 3i minus 2i, which will give you just i. Just my bad, basically. Okay, so the subtraction addition works intuitively. You do this, you do the addition and subtraction on real part and imaginary part separately, and then you write them together. So how would the multiplication would work out? Well, it's also a little bit intuitive. Okay, let's have an example. Let's say that we have 5 plus 2i multiplied with 3 plus I. Well, here you don't multiply the real parts and the imaginary parts separately with itself. You multiply as if you are opening a bracket. Okay, how do you open two brackets when you multiply? You multiply 5 with 3 first, and then you multiply 5 with I, and then you multiply 2i with 3, and then you multiply 2i with I. Let's do one by one. If I multiply 5 by 3, I would get 15. If I multiply 5 with I will get plus 5i. If I multiply 2i with 3, I will get 6i. If I multiply 2i with I will get 2i squared, right? Okay, so let's simplify this. We have 15, perfect. We have 5i plus 6i, which is 11i. Okay, now we have 2i squared. Remember that I told you that I is actually root of -1. So if I take the square of it, I squared, it would be -1, right? So instead of I squared, I can just write -1, right? So it is just 2 times -1, which will give you -2. So I write here -2. Okay. Okay, now let's simplify further. You have 15 and -2, so 13, and then you have 11i. This will be how you are multiplying your complex numbers. So it's also intuitive. It's just as opening brackets when you multiply two brackets. And just keep in mind that I squared is equal to -1, and they use this fact to simplify your expression even further. Okay, there is also part with the division, but we will come to that after a while. Let's first focus on how do I deal with the higher powers of I. Well, how do you deal with that? It's first you have to observe what happens when you take the powers of I, and then you will understand it eventually, intuitively. How do you deal with the higher powers of I? Let's say that we have maybe a better color. I always use orange for some reason. Let's say red. Okay, so I equals to I to the power of 1 equals to I. We know that. I to the power of 2 equals to -1. We know that as well. But I to the power 3. Well, it is just I squared times with another I, right? So -1 times I will be -I. And then you have I to the power 4, which means you are multiplying -I with another I. Okay, so what happens? -I times I is -I squared, but I squared is -1 already. So this is -1 which gives you plus 1. So I to the power 4 is actually 1. Now, if I continue again, I to the power 5 will be equal to I to the power 4 times with another I, which means 1 times I, then you have just I. Now, you see that there is already a pattern. After every 4 power, you have the same result for the powers of I. Okay, so you have I minus 1 minus I1. Then you will again have I minus 1 minus I. And if I scroll down a little bit, or oops, if you go down, it will be basically 1. Okay, let me fix my camera very quickly. Here you go, that's me. Yes. So there's a pattern basically there. So if you want to find, for example, I to the power of 79, how would you find this? Well, first, you know that every 4th power is equal to 1, right? So I to the power 4 is equal to 1. I to the power 8 is equal to 1. I to the power 12 is equal to 1. I to the power 16 is equal to 1. So what's the largest number that's divisible by 4 inside 79? Well, if you take, for example, 72, that's divisible by 4. 76 is divisible by 4, and there's nothing more than that. So you have this is equal to I to the power 76 times I to the power 3, because powers are added as in normal multiplication. But I to the power 76 is just 1. Why? Because every 4th power of I gives you 1, right? And I to the power 3, now it's easy to calculate, it's just minus I. So you have 1 times minus I, the final result will be minus I. So that's how you calculate your higher powers of I. Okay. Let's move on. We will talk about the complex conjugate and then finally talk about the division of the complex numbers. We talked about the addition, subtraction, and multiplication. But in order to be able to talk about the division of complex numbers, we have to talk about the complex conjugate. What's the complex conjugate? Well, complex conjugate is very simply defined, okay? By notation, they usually use star. So if this is your complex number, then the complex conjugate of this complex number would be z star. That's how we define it. And it's simply defined as to be a minus bi. So nothing changes at all except the sign between a and b. Okay. If you have, of course, minus, then it would be plus. Basically, plus becomes minus and minus becomes plus. And that's all it means to be complex conjugate. Okay. And I will not even go to the details of it because that's literally everything that you need to know. Okay. Although this is a crucial, there's a crucial tip by using these two definitions in the division. So, for example, let's say that you are dividing 5 plus 2i by 2 plus 3i. How would you divide these complex numbers? Well, in order to divide a complex number with another complex number, you have to multiply that division by the conjugate of the denominator, divided by the conjugate of the denominator. So you need to have 2 minus 3i multiplied by 2 minus 3i. Why we need this? Okay, first of all, before we come to the reason, you realize that 2 minus 3i divided by 2 minus 3i is just 1, right? So multiplying division with 1 is actually nothing, right? It's just a multiplication by 1 and nothing changes. But why we do it then? What's the reason of us for multiplying with such a weird number, like with the conjugate of this denominator, right? 2 minus 3i is the conjugate, complex conjugate of 2 plus 3i. Why do we do it? Because after you multiply, you will realize that in the denominator, you will have only real number. Okay, let's see how it works out. So let me first multiply 5 plus 2i with 2 minus 3i. So I have this multiplied by 2 minus 3i. Okay, that would be equal to 5 plus 5 times 2 is 10. Then you have 15i, 5 times 3 minus 3i. 2i times 2 is 4i. And then finally you have 2i times minus 3i, which will make it minus 6i squared. Okay, so then you have 10 minus 11i. I squared is minus 1. Minus 6 times minus 1 is plus 6. Okay, so the answer is 16 minus 11i. So here in the numerator, you will have 16 minus 11i. What will happen to the denominator? Well, let's have a look. Let me delete this part. 2 plus 3i times 2 minus 3i. Again, let's open it up. 2 times 2 is 4. 2 times minus 3i is minus 6i. 3i times 2 now is plus 6i. Right? And then you have 3i times minus 3i, which is minus 9i squared. Now you realize that you have a minus 6i and plus 6i. So this will just simplify. And you have 4 minus 9i squared. But I squared is a real number because I squared is minus 1. Minus 1 is a real number. Minus 1 times minus 9 is plus 9. So you have 4 plus 9, which will be equal to 3. So in the denominator, you will have 30. Okay. Now you see the reason why multiplying these numbers, well, complex number and the complex conjugate of a complex number will give you a real number, because you are getting rid of the i's and you are also getting rid of the I square, because I square is actually minus 1. And then finally you have only real number here. Okay. But that's not the end, by the way. So what we have to do following this, so let me delete this part again. This is not a complex, this is not the Cartesian form of a complex number. Remember that the Cartesian form of a complex number is a plus bi, right? So they have to separate. How do we separate this fraction? Well, we write 16 divided by 13 minus 11i divided by, 11i divided by 13. Right? I just separate the numerators into two fractions. And this is my complex number after division in its conjugate, in its Cartesian form. Sorry. Okay, that's how we divide the complex numbers, and that's end of the first chapter that we were looking for. Okay, now I'm gonna delete the screen and check the second part. Maybe in this today we can go to over the basics of the complex numbers, and the next time we talk about the further details about complex numbers. Let's see how it goes first. So modulus argument. Let's talk about this a little bit. How do I find the modulus of a complex number? Well, it's defined to be it's denoted with the absolute value. So if your complex number is z, then you put it under between two lines, okay, like an absolute value, and that could be defined as a squared plus b squared, where your z, of course, is equal to a plus bi. Okay, so basically you take the square of your real part, square of your imaginary part, and then you take the sum of it, and then you square root of it. For example, if z equals to 2 plus 3i, then your modulus would be root of 2 square plus 3 square, okay, which would be root of 13. That would be your modulus. Okay. What are the features about this modulus? Well, there are only few features that we really need. I don't think that we really needed much, but let's have a look. If you multiply a complex number with its complex conjugate, or the vice versa, which is the complex conjugate times the complex number itself, okay, it's the same thing, then this would be equal to the square of your modulus, okay. You can check this out. I will not do it on the screen, but try to check this out. Take a random complex number and multiply it with its conjugate and see if it's really the square of their modulus. You know the definition of the modulus, which means you can take the square of it. You know the definition of the complex conjugate, which means you can multiply these two numbers, see if the equality holds or not. I guarantee you it will hold, of course. Okay. Okay, I'm not sure if we really need to go here. How do I find the argument of a complex number? I need to explain you what argument is. It's actually defined in the third chapter, but I will explain you this very quickly. Another notion that we need about the complex number is the argument. Okay, how it works? Well, we define complex numbers geometrically on a xy coordinate in the following way. Let's say that this is your xy coordinate. Okay. Again, we define the complex numbers geometrically in the following way. And your x-axis will be your real part, and your y-axis will be your imaginary part. For example, if we write 2 plus 3i, if we want to show it on this xy coordinate, we find 2 on the real part, because real part is 2. Then we find plus 3 in the real part, which is here. And then we find, of course, the point, which is this point. And then we draw a vector from the origin to that point. So let's say red, from origin to that point, like this. And this is how we define and write our complex number in geometric way. And you can check this out. This distance, the length of this red line or the vector is actually what we found as the modulus. Okay, why? Because this is a hypotenuse roll, right? This is 90 degrees. Here you have the real part. Here you have the imaginary part. So if I take the square of 2 and square of the 3, it will give me hypotenuse, right? After I take the square root, right? It will give me hypotenuse. But the hypotenuse is this red line, right? Which is also your modulus. Okay. Another way of defining modulus would be geometrically, would be the length of this line, basically. And the argument that we defined is that we all the time say is actually the angle that you have here. Angle that your vector makes with the real part. That's your argument. That's your argument. That's your angle that you're looking for. Okay. So we have here how do I find the argument of a complex number? That's how you find it. What features should I know about the argument of a complex number? This part is not exactly important. I will skip it. What are the rules for moduli and the arguments under multiplication and division? So what happens with your arguments when you multiply or divide? Well, the following. So I don't need to write it anymore. So let's say that you multiply two complex numbers inside modulus, right? So you are first multiplying them and then trying to find their modulus, right? That's the same thing as finding the modulus of them separately and then multiplying them. There's no difference. If you do the division, it works the same idea. If you divide two complex numbers and then find the modulus, it is the same as finding the modulus first and then dividing them. Okay. Again, modulus was defined to be here, like this one. You take the square of the real part and the square of the imaginary part, and then you take square root of it. Okay. And the angle, how would angle work? So if you multiply two complex numbers, and if you want to find the angle after multiplication, right, as here, then that would be just simple addition of the angles of two complex numbers. If you want to do the same for a division, so let's say you are looking for arc z1 divided by z2, then that would be basically arc of argument of z1 minus argument of z2. My handwriting is off right now, but yeah, you got the point. So when you multiply two complex numbers, the angle or the argument that you're looking for will be the addition, sum of these angles. When you are dividing them, of course, it would be the subtraction, so the argument z1 minus argument z2. Okay, so let's move on. Let's see what else we have. Well, that would be all for the second chapter. So the final chapter of the first part would be introduction to Argand diagram. The Argand diagram is the diagram that I drew for you previously as the xy coordinate, where x coordinate is your real part and the y coordinate is your imaginary part. So that's basically it. And there are a few things that we need to know about this. So I will skip these two parts, by the way. That's all fine. That's also fine. So there's nothing much actually to do here, except I want to explain you how to deal with the complex numbers in certain cases. For example, if you have root of -9, how you can convert this to something with I. Okay, well, we use the property of the root, where root -9 is actually root 9 times root -1, right? We can always do this with the roots. We can separate it into its factors, both under the root. Okay, 9 times -1 is -9, so we can write them separately under the root. But root 9 is 3, and root -1 is I. So 3 times I is 3i. So root -9 is actually equal to 3i. So this fact is just a little tip. to deal with quadratic equations if there is no real root or etc. But it's just important to keep in mind that you can separate the root into factors, but both factors should be under this under the root as well. Okay, and then of course then you simplify. Root 9 is 3 in this case. Root minus 1 is I, so the answer is 3i. Okay, let's see what we have. Further complex numbers, geometry of complex numbers, which means the Argand diagram, how we add them in an Argand diagram. Let's assume that we have a complex number given in the screen like this. So W and Z. So this is Z, this is W. And these are the W is this vector and the Z is this vector. Okay. And when we add them, we just do the vector addition. Okay. You can use geometric addition of vectors, or you can notice this. So this W is actually 5 because the real part is 5, plus the imaginary part is 1i, so you write I. This Z here is, so the real part would be 2, it corresponds to 2, and the real imaginary part corresponds to 6, so you write 6i. Okay. How do you add them? Well, you add them as usual. So 5 plus 2 would be 7, I plus 6i would be 7i, and that would be your addition, z plus v. How do you write it down in sketch it down in the geometric way? Well, you find the 7 in your real part and the 7i in your imaginary part, and you find your point, and then you draw this red line. That would be your addition. It works the similar way in the subtraction. Okay, you just subtract them as usual. So z minus v, and then you find the coordinates, and then you find the point, and you draw a line from the origin to that point. And that would be a vector, of course, representation, and that would be subtraction. What else we need? There's, of course, multiplication and division, and how we actually deal with them. So it's a little bit confusing, maybe this part, but bear with me. So it says that geometrical effect of a multiplying a complex number by a real number a will be an enlargement of the vector by a scale factor a. So it means that if you have a complex number, let's say 5 plus 2i, and if you multiply this with a real number, let's say 2, you are just enlarging your vector 2 times, right? So your it will be 10 plus 4i. So in your xy coordinate, you just go 10 to the right instead of 5. You go 4 to the up instead of 2. So you are enlarging your vector by 2 times. If you divide it, if you multiply the fraction, then again, it's still enlargement or stretching, you can call it, by the factor of 1 over 2. Okay, so it's enlargement by the factor of 1 over 2, or it's stretching by the factor of 1 over 2. Okay. That's the first thing. So geometrical effect of dividing a complex number by a real number, again, as we said here, geometric effect of multiplying a complex number by I, imaginary number I, will be rotation of 90 degrees counterclockwise. Okay, let's say that you have, again, 5 plus 2i. Okay, 5 plus 2i would be, so 5 is here, 2i is here, which is here, so you have this vector, that's your geometric representation. Now, if I multiply this by 5i by 5 plus 2i, what I will get? I will get 5i plus 2i squared. 2i squared is minus 2, right? I squared is minus 1. Minus 1 times 2 is minus 2. I have 5i minus 2. I will write the minus 2 first and the 5i because I usually write real numbers first. I have this number now. So if I do sketch this on my Argand diagram, what I have? Minus 2 is here and the plus 5 is here. This is the point, and this is my new vector after multiplication. And if you check it out, the angle between this red and the blue vectors will be 90 degrees. And it is counterclockwise. So the geometrical effect of multiplying a complex number by imaginary number I will be just rotation counterclockwise of 90 degrees. What else? Geometrical effect of multiplying a complex number by imaginary number AI. Okay, so will be a rotation, of course, because you have I by 90 degrees counterclockwise, but also enlarging it by A. Because when you multiply a complex number with A times I, right, and then you have a complex number, okay, this means rotation counterclockwise 90 degrees. This means enlargement by A, and you do both, and then you have your new geometrical vector shape, which is a vector as well. Okay, let's see. Yeah, that's okay. If you then, so the final thing is the geometrical effect of multiplying or dividing a complex number by a complex number will be an enlargement and the rotation as well. Okay, then you will have the direction of the vector will change. The angle of the rotation is the argument. Distance of the point from the origin will change as well. The scale factor is modulus. So this part is more, let's say, complex compared to the remaining ones. It's important that you keep in mind the direction of the vector will change. Direction is a very important factor in the geometry. So the angle of rotation will be your argument. So how much you will rotate is actually the angle that you're having. And then the distance of the point from the origin will also change. And the scale factor will be just your modulus of your complex number. So this part is more complex compared to the previous parts, but for these, it's important to have practices, okay? Which I will do in next lectures, maybe separately. But here I try to keep the samples as or the practice questions as simple as possible. For now, I will skip this. There's more. Maybe in the next lectures we will have an example of this. But the rules are the rules. Basically, it will not change just because you have a complex question, let's say. You'll still have to apply the rules, right? Okay. What else? What does a complex conjugation look like in an Argand diagram? And the answer is very simple. The geometrical effect of plotting a complex conjugate, right, on an Argand diagram is a reflection in the real axis. Okay. So basically, complex conjugate was if your complex number is a plus bi, complex conjugate would be a minus bi. And this is just, again, reflection in the real axis. Why in the real axis? Because a plus bi, let's say, is here, right? Then the conjugate would be the same same a, but the negative of the b, which is here, right? So as you can see, it's just a reflection on the real axis. Okay, simple. Okay, that will bring us to the end of the second part, or the first part of the second part. And finally, we have the forms of complex numbers. I think I will leave this one, or let's see if I can actually cover this. Why not? We have two forms. I will make it quick. No, I will leave this for the next part, for the next time, the forms of the complex numbers. This is rather very important, and I will mix this with the questions which we can solve. Okay, so until here, you have all the introductory part of the complex numbers, the forms of the complex numbers, which are very important. Okay, I will talk in the second chapter or second part of the video, let's say on YouTube, or in the second lecture, third lecture in the order, of course. Well, yeah, that would be all. I will end the screen recording and then ask if you have any questions. Then you can ask me your questions. Again, for the people who are watching me on YouTube, the remaining part, forms of complex numbers, not the applications of the complex numbers, just the forms of the complex numbers will be in another video, and probably next week, I guess. I'm a little bit sick nowadays, but we will see as soon as we can, at least. And then we will move from that maybe to matrices. Why not? Yeah. Okay, I hope you liked the lecture, and please don't forget to join my Discord server and ask me really as many questions as you want. Also, don't forget to like and subscribe in YouTube, and yeah, thank you all, and see you later.